Now we'll do verification of maximum power transfer theorem for a given circuit. So now here I will take the same circuit which we did for Thevenin's equivalent circuit and Norton's equivalent circuit. Those who are not seeing that video, you can check that video. So here the question will be find the value of RL. So this will be RL. This R4 in the problem they will give it as RL. Find the value of RL. They will not give. They may not give what is the value of RL. Okay, they will give just a variable part. They will give. You need to find out what is the value of for what value of RL you are going to get the maximum power and what is that maximum power. This is the theory questions also. Any circuit let them give. We already have not Thevenin's theorem. With the help of Thevenin's theorem, we can convert any complex network into simple circuit with one voltage source in series with a resistance. So once the circuit is easier, you can connect that RL, and after that the statement of maximum power transfer theorem is maximum power is delivered to the load from the source when the load resistance is equal to source resistance, the internal resistance of the source. So if I convert any complex network into voltage source in series with resistance, we can consider that as a voltage source with internal resistance of RTH. Okay, voltage value is RTA VTH, internal resistance is RTH. After that, if I connect RL, maximum power will be transferred to the load RL from the source VTH, Thevenin's equivalent voltage, when RL is equal to RTH. So question mark they will ask for what value of RL means just find out RTH for a given circuit. That is the value answer for RL. After that, what is the value of that maximum power is given by P is equal to VTH whole square voltage square divided by 4 into RTH. Okay, 4 times RL or RTH. RL is equal to RTH, no? 4 times RTH. That is the value of maximum power. So now we'll verify that for this circuit. Assume that this 20 ohm is not given, just it is a variable resistor. For example, I will replace this with that component only. A variable part I'll put here for better understanding. So here variable resistor is there, no? We don't know what value of RL, no? So I can put that there. So this is, we don't know for what value of R4 you're going to get maximum power here. Okay, now this is a complex circuit. We have to find out, okay, VTH, open circuit voltage across this. So we have to remove that RL. Okay, we have to remove this RL and you have to find out open circuit voltage. So this is a circuit I did for Norton's theorem. So I am removing the RL. This R4 we are considering as a load because we are finding for what value of this R4 maximum power is transferred. So this remove this load and you have to find open circuit voltage here. To find open circuit voltage, you can connect your voltage. You can connect probe with respect to here. It will measure, or you can also find potential difference here. Differential voltage. Connect one probe here, another probe here. Then you have to take difference between these two. Okay. Or another method I did in multimeter. You have to connect multimeter and you have to set that multimeter to volts. By default, it will be set to volts only and connect positive to here. We are measuring. We removed load here. We removed load here. If you want, you can rotate this by right clicking and rotate 90-degree clockwise. And this multimeter by default it is V. If you want to use it as a meter, you have to click A. If you want to use it as a voltmeter, V. If you want to use it as a ohm meter, then ohms you can select. So now let us check what is the VTH value. I think we already calculated in the Thevenin's theorem only. You should get 66.66. Okay, 66.66 is coming here. This we already got in the Thevenin's theorem. Same circuit I am reusing it. And to find the RTH, okay, to find the RTH, remove the current source because we have to make the all the sources to 0. So this entire path is removed and voltage source is short circuited. So here also it will show, the meter will show this is kept at ohm. This is kept at ohm. So it is showing 13.33 is the RTH value. After that, we are having Norton's equivalent. So I don't want Norton now. So I will write I will okay, this current source I removed and I have to connect RL, RTH I have to connect. Now in the Norton's theorem I renamed it as RN. Again I will rename it as RS. S stands for source resistance. If you want you can save it as source resistance RS. Since we reduce this one to Thevenin's equivalent circuit, I am writing RTH and VTH only. RTH to rotate, right click and rotate right side 90 degree or control R press. You can press control R button also. And voltage source. If you want to place voltage source, place component. It is available in the group sources, then DC sources, power source, DC source, DC power. This is VTH value to set. VTH value is 66.66. So change this value to, by default 12 volts will come. So this one you change it to 66.66. This particular circuit we found out open circuit voltage with the help of voltmeter connected across open circuit load terminals. We got 66.66. So value you have to change this one to 66.66 and label as VTH. After that complete the circuit because there is no open. With the help of mouse you can complete the circuit. Again to find the current value you can use ammeter in between these two terminals because ammeter should come in series. Otherwise you can connect a current probe. Current probe is there. You can click this and you can get it. I already placed it, so press escape. So now actually maximum power theorem states that maximum power is delivered to this load from these two sources when the value of this will be equal to RTH. That is, you have to write Thevenin's equivalent circuit with voltage source and resistance. So same value of resistance you have to put here, not 20 ohms. You have to change that instead of that part, no, that part you have to adjust potentiometer shown now in the first circuit. That you have to adjust to 13.33 only. Then only you are going to get maximum power there. 13.333. Okay, now you can find out the power. Power is equal to, I think here, this is power. You can directly find out. You can find out power in the RL. So now you can see with RL is equal to 13.33, you are getting power of 83.3 watts, and current in the circuit is 2.5 amps. So now this is will verify with the help of graph also. For different values of we have to vary the load value here. This is a part now. You have to vary a value of resistance from 1 ohm, because this ohm is 13.33. So you have to vary the resistance from 1 ohm, 2 ohm, 3 ohm, 4 ohm, 5 ohm, 6 ohm, and you have to get to 20 ohm. So for which value of, every time you have to find out current, and here you have to use part, and you have to vary each time. You have to note down current and voltage. You have to find out the power. For what value of R you are going to get maximum power, that is the theme. Now for that you have to go for parameter analysis. Go to simulate, analysis and simulation. Go to parameter sweep. You go to parameter sweep, then parameter, device parameter, we are going to vary resistor value now. So select resistor value, name of the resistor, we have to vary load now, RL. RL you have to set here, RL is there. You have to use RL. You are going to get all these resistors, because in the entire sheet we are using all these resistors. We have 4 circuits now, first circuit, second circuit, third and fourth. Each resistors are having different names. Okay. So this resistance is we renamed it as R load, so you have to select same R load. And parameter is resistance only. And present value is 13.33. We set at this value. Otherwise, just write a variable resistor only. And after that, we have to start the value of resistance value from 1 ohm, and stop value is some 25 ohms. And increment you can give with 0.1. Okay, first is 1 ohm, next 1.1, next 1.2, next 1.3, next like that, 2, 2.1, 2.2, like that. Next 3, 3.1, 3.2, 4, like that. You are going to get around 241, 41 points. So let me take 3 at least. Okay, if I take one only, exactly will get. Okay, let us analyze. So now this analysis sweep should be DC operating point. Analysis to sweep is DC operating point. So meaning of that is we kept voltage as VTH value. We kept RTH as 13.33. This R load is actually variable. So that you have to take as a sweep parameter, parameter sweep. That value is resistance value you are sweeping. The name of that is R load. parameter is also resistance. Present value here I already set this value to 13.33. If you don't know what value you have to put here, just write uh, whatever default value is there, no, that only you can put here. After that, just run this. So you can display it graph in, display the results on a graph. So you should get a graph of 241 iterations will takes place. Okay. So actually here you are getting I will use extra things. I have to remove this. 1 minute. I'll stop this. This it is doing so much here. This is actually current value. Current value I don't want. Okay. IPR2 is current value I don't want. I want only power PR4. Okay. So one more thing I want to forget here. Okay, see here. You can use cursor. Show cursor. To cover all. I did something else. I'll redo it once again. So one more thing I want to forget. Parameter, no? Once you select parameter sweep, once you select this analysis and simulation parameter sweep, resistor is selected or load. So you are getting output because one more important thing is you have to go to output tab. This is output tab. In the output tab, which one you want to plot, you have to give here. So previously two graphs are coming, no? So here we used this two probes. I don't want current, so you can remove this current value. So you click on the IPR to remove it. So power across probe PR4, or you can also do P of resistor RL. You can see here P of RL, I of RL is there, I of R load is there. Similarly, P of R load is there. No, this also you can give. Okay, P of R load also you can try it. If you use power this wattage meter, automatically it will take that probe values. If you don't use this watt meter, then which resistor is this? That label you see, P of that label. For example, here R3 is there. Then you have to take here P of R3. You have to click add button. That should come here. Now run this. Now actually only one output will come, which is power. Previously two graphs were coming, current versus that. So it is actually plotting for different values of RL, starting from 1 ohm. X-axis you see, x-axis is resistance. It did for 1.1 ohm, 1.2, 1.3, 1.4, 1.5, 6, 7, 8, 9. Here 2, 2.1, 2.2, 2.3, 2.4. Like this. Next to 3, 3.1, 3.2, 3. Next to 4. Like that. Here you can see. Now you can find out for what value of, or here you can see exactly at 13.3. Exactly here 13.3 you are getting a maximum power, and that maximum power value is 83. Here 80 is there. So if any marker is there, let me see. show grid, show let's say okay, show cursors. Okay, both are actually disabled. If cursor are there, we can show what is the value here. Exactly, it will come here only. 1 minute, I will try to see. Okay, here exactly 13.33. You're getting maximum power that is equal to 83. So that here also you can see in the circuit. Okay, power meter value. Power is also 83.33. So this is graph. Maximum power is obtained at here, and this value is what is actually using sheet values visible on it. So that's if you don't use that, you can see power here only. So the formula for that power is VTH square divided by 4 into 13.33. VTH square divided by 4 in RTH. You can also tabulate the waveform the readings. So go to parameter sweep. Parameter sweep, then select already values are there, no? You select this and output is P of R load, otherwise P of this probe 4, PR4. After that, here in the analysis parameter, instead of display the result on graph, you can also display the results in a table, which will plot a graph for different values of resistance. What is the power? It will show the table of, see, so much reading, 241 readings will come. For resistance 1, this is the power. 1.1, this is the power. Exactly at 13.33, you will get maximum power of 83. After that, if you increase, again power will decrease. Still, it will plot 241 readings. Otherwise, you can do faster by increasing the resistance step size. Instead of 0.1, you can give 0.2 or 3. So it will increase faster. It is actually going on. After completion of all the 241 values, you can see for what value of RL you are going to get. Let me change parameter sweep to increment the value with higher value. Step size instead of 0.1, I'll increase little bit more. Starting value is 1, final value is 25. Step value is, let me give some 0.4. Okay. It will take 1.4, next 1.8, like that it will take. First is 1, step size is 1.4, next 1.8. So now at approximately 13.3, you can see here. 13.38, 13 point is plotting actually. See here. 13.3, you're getting 18.334. Again, if I increase this to 13.8, it is starting reducing. Okay. The graph is increasing, reaching maximum at 13.33. Again, if I increase the resistance, power will reduce. At 25, power is reduced to 75. At one resistance, power is 21, reaches maximum to 83 at 13.33 and reaches a value of 75 at 25. Still, if you increase this one to last value, if you give 50 or 100, then this further the value of power will be, you can get still less power. Okay, thank you.